All right, it's time. Welcome back. Can you believe it? We only have, I think, 3 more classes of our regular class, including today. We got this weekend, this time, and Friday, and then a week from today, and then the last Friday of the semester will be our final meeting, and that will be our last in-class test. So I hope everybody's clear on how the tests are going to go. That last test will have this last new stuff on it, the graph theory stuff. And then, in theory, you could have finished all of your checklist items on that last day of class, and then you won't have to come to the final at all. That probably will not happen for most people, but for those of you who do still have check marks left over for the final exam, you will only have a few problems to work on the final, probably just whatever you're catching up on. So the test 1 week from Friday will have problems that everybody needs to do, and then the final exam is just for catching up. And if you don't have anything to catch up on, then you don't have to take the final. Any questions about that? Does that sound all right? The final exam lasts 3 hours, although you probably will not need the 3 hours. You could probably do every check mark in 3 hours if you had to. Let me know if you have questions about that. Some people have started to get a little worried if you have a lot of things to make up before the final exam. Some people have come by and chatted with me. I would be happy to get together with anybody and go over old topics if there are things that still are not making sense to you. Let me know. We can meet by Zoom or in my office, whatever you like. All right, so let's get on to the next thing. The next thing that we're going to talk about in still on the topic of graph theory is another type of special kind of circuits. We have been talking for the last 2 times about Euler circuits and about minimum duplication circuits. Those are circuits which use every edge and not repeating any edge. Or in the case of the minimum duplication, they would duplicate as few edges as possible. Today I want to talk about the same kind of a thing, but it is circuits which don't duplicate any vertices instead of edges. That's the only difference. It turns out to be a completely different kind of question, and actually this is a little bit more useful in real-world applications of graph theory. So unfortunately you have to remember there's just somebody else's name on this. This is called Hamilton circuits. Hamilton circuits. This is Hamilton the mathematician, not Hamilton the American politician rapper. The Hamilton the mathematician is from Ireland. I think he lived in Dublin, and he is known in mathematics for many things. One of them is his work in graph theory. He's better known for things in like calculus type settings, and something he invented became very important in quantum mechanics, even though he worked before that existed. But anyway, Hamilton circuits. This is a circuit which visits every vertex once with no repeats. I will say no repeats except the start and end, right? It's a circuit, so it ends up at the same place where it started. But as it goes through the graph, it hits every vertex of the graph, but doesn't hit any vertex twice, apart from ending up at the same place where it started. All right, that's called a Hamilton circuit. Vertex, it's the only difference. So Euler circuit uses every edge once with no edge repeats. Hamilton circuit uses every vertex once with no vertex repeats. That's it. That's the difference. Hamilton circuits also cannot use any edges twice. That's because if you repeated an edge, then automatically you would have to repeat the vertices at the 2 ends of that edge. So actually, Hamilton circuits also don't repeat edges, but you don't really think about it in those terms anyway. So, for example, here is a graph. How about this with an extra edge over there? This is a graph. Is there a Hamilton circuit? Can you make a circuit in this graph? You don't have to cover every edge. You just have to meet each vertex once. Anybody looking at the picture, can you see? It's not so hard to find a Hamilton circuit in this one. What do you think?
Yeah, it's possible because you can just go one time around.
Yeah, how about just go around the outer edge? That makes a Hamilton circuit. So if I want to, it doesn't really matter, but let's say I'm going to start at the bottom. I go like this, around that one, like this. That's it. That's a Hamilton circuit, all right? You might feel like I missed a bunch of stuff, and yeah, I missed some edges, but that doesn't matter, right? Hamilton circuit means you hit every vertex with no repeats. So maybe I'll say this parenthetically. May miss some edges, right? You don't have to hit all the edges. That's not the point of a Hamilton circuit. You just have to use all the vertices, all 4 vertices. All right. This is important in the real world. Actually, this, like I said, is a little bit more important in the real world than Euler circuits, which are about hitting every edge. This, if I wanted to, for instance, visit my 3 different friends who live in 3 different places, I don't care about how I actually get from one place to another. I just have to end up at each of those 3 friends one time and then come back home afterwards. All right. You don't have to walk along every possible street or something like that. I just got to visit the 3 vertices. Okay, how about, here's another example. Basically, all we're going to talk about today is if I draw a graph for you, can you find me a Hamilton circuit? Or explain why there is no Hamilton circuit. All right, how about this one? Let's find a Hamilton circuit in this one. I think I can. Anybody see how you can do this? You might be tempted to just go around the outside edge again, but actually there's a vertex in the middle that you're going to miss if you do that. So perhaps a slight variation of that. Any ideas? Yeah? Go across the middle. You mean like this?
Yeah.
And then I think actually this is not a great idea. At this point I can go like that, but then I'll be stuck here. Because remember, you can't repeat a vertex. Another idea.
You maybe start at the top and go fully around to
Yeah.
the right,
Uh-huh.
and then go down. Or you could do that.
Is that what you meant? Sorry.
Yeah, that's fine.
Yeah, okay.
And then you can go up the top,
Okay.
to the middle, and then go down.
Okay. This hits every vertex, but I want it to be a circuit.
Oh.
These are all close. Yeah?
You start at the middle and then go diagonally up to the right.
Yeah, you got to use the diagonal. So I think what he said is the same as that, right? Is that you can draw this as if you were starting at the middle and go around like this, I think is what he was saying. Yeah, this is great. You got to use the diagonal in this one. Although, I mean, it's not immediately obvious when you first look at it that you need to use the diagonal, but in fact you do in this example. So that is also a Hamilton circuit. One nice thing about Hamilton circuits is they are quite a bit easier to draw than Euler circuits. They are easy to draw. Like that one, really most of the time when I draw these, I'm going to draw it by sort of scribbling in some edges here. I know I'm always using this color. Like that, right? This describes what the Hamilton circuit is. Now, in an Euler circuit, it can be very confusing to draw the lines. I tried to talk about that last time, and you'll see when you try to do the homework. Drawing the lines in a clear way on an Euler circuit is quite confusing, but it's not so confusing on a Hamilton circuit because really you're only using every vertex once, so it's always clear. For example, once the circuit gets to here, if you start here, once you go here, where do you go next? Well, obviously you go next here, and then here, and then here, and then here. There's no ambiguity because it's not like your path is like crossing over itself or anything like that, because you're not reusing any vertices. So usually I'm just going to draw it like this. I didn't even indicate where the starting point is or what direction it goes. Really, none of that matters all that much. What I care about is what the circuit is, which edges it uses. All right, they are easy to draw. How about this one? So the big question is, if I draw you a graph, can you tell me, does it have a Hamilton circuit or not? How about that? Now this is similar to the one above, but it doesn't have that diagonal. I drew it long. There's no reason for that. Just a square, just like this one up here, but there's no diagonal there. Actually, this one, you have an idea?
I would set in the middle.
Yeah.
Go to the left.
All right.
Go down.
Mm-hmm.
Right.
Mm-hmm.
Up.
Like this?
Yeah.
Okay.
Left.
Whoa, sorry. All the way?
Yeah, and then down.
That.
Oh, do you have to start at the same point?
Yes, it has to be a circuit.
Oh.
So actually, this is no good because I made a circuit here, but I revisited this vertex. Right? I had visited before, and then I arrived at it again. Yeah, actually, that is no good. This one, it turns out, does not have a Hamilton circuit. This covers what I drew right here, covers every vertex, but it's not a circuit. To make it a circuit, you have to end up back in the middle, but actually that's not possible to end up back in the middle without repeating any of these vertices. So this one right here, I'm just going to erase that. This one has no Hamilton circuit. No Hamilton circuit, but I'll say, can I just say, hard to say exactly why. Now, when we talked about Euler circuits, I hope you remember, there is a simple way that you can tell if it has an Euler circuit or not. It has to do with the degrees of the vertices. And the simple trick is, if all the degrees are even, then it does have an Euler circuit. And if not, then it doesn't, right? There is no similar trick for Hamilton circuits. There is not an easy thing that you can just look at in the picture and immediately tell if there is or is not a Hamilton circuit. Unfortunately, you have to think quite a bit more in depth about these to figure out. So that one has no Hamilton circuit, but like I said, it's hard to say exactly why. What if I make similar picture but slightly wider? Like this. Actually, this one now does have a Hamilton circuit. I just made it stretched out a little. Can anybody see how you can do it in this one? Let's start up here. Anybody want to tell me how you would go about it? Maybe someone I haven't heard from yet. Yeah.
Go down, just wait, never mind. We go to the right ones,
Okay.
then down,
To the middle?
yeah, then
Uh-huh.
right, then back up,
Yeah.
then to the right.
And now we go all the way around, right? Yeah, great. That does it. So that's a Hamilton circuit in this graph. It's impossible on this one. It is possible on this one. What's the big difference between these two? The answer is, I don't know, it's complicated. There's not a really simple thing that you can look at and say, yeah, obviously this has it and this one doesn't, all right? It's complicated, but that's what we're here for. Here's just one last example. What if I have 2 points on the left side and 4 on the right, and I'm going to connect up every point on the left to every point on the right? This one also, and all the intersections in the middle don't count as vertices. So it's just, there are a total of 6 vertices here. There's the 2 on the left and the 4 on the right. This one also is not possible to do a Hamilton circuit. If you think, this one you can kind of reason it through. For example, if I were to start on this guy up here, and I'm going to try to cover every vertex by edges. My first trip across, I got to go over to one of these 4, and I don't know which one. Let's just say I go over to the top one. Then my next edge has to be this one, right? I have to come back across to the other guy. Okay, then maybe from here I have to go back across to the right-hand side. Let's say I go to this guy. And here we get stuck because at this point The only edge available is going back over there, but that's a vertex that I already visited, and that's not allowed in a Hamilton circuit. You're not allowed to revisit any vertex until you're completely done with the whole circuit. All right, but I haven't finished because I missed out on those two guys over here. Right, these guys never got any edge on them. So this one here has no Hamilton circuit. Also, that's a little more complicated. All right. Any thoughts about this so far? This is Hamilton circuits. It's not a complicated concept. I mean, the idea of it is not hard. It is a little tricky to figure out when there is or is not a Hamilton circuit. Our tools are basically going to be based on two very simple observations. And I will tell you the first one. They're both pretty obvious. In a Hamilton circuit, for example, maybe I'll redraw one of those that we saw before. How about this one, where it went, I'm going to scribble them in like this, around like this, and then down the diagonal, back up the middle, like that, right? I will have you notice, in a Hamilton circuit, each vertex, those are all these points, each vertex meets the red line on two edges. Do you believe me? I believe me. Each vertex meets the red line on two edges, okay? This is the obvious observation. In a Hamilton circuit, each vertex meets two chosen edges. I mean, two edges that are actually being used in the circuit, all right? Each vertex meets two of them. It's because the circuit has to go through that vertex only once. So it arrives along one edge and then leaves along another edge. And that's it. So 2 times. You could think of this in terms of the degree. It's kind of like for each of these vertices, its degree, if you only consider the red ones, is 2. They all have degree 2 if you're only looking at the red ones. All right? In a Hamilton circuit, each vertex meets 2 chosen edges. All right? And this actually can help you create a Hamilton circuit in a graph without any guessing. So this means if some vertex has degree 2 in the original graph, the OG if you will, then our Hamilton circuit, come on now, must use both of those edges. All right, I'll show you what I mean by this. This is actually a very, once you look at it properly, an obvious fact, but it actually helps you a lot in terms of building a Hamilton circuit. For example, let's say I have this graph here. Let's try to build a Hamilton circuit without guessing. All right? On a small example, you might be able to just sort of look at it and guess the answer, although that's not something you want to rely on in general. In mathematics, you don't want to rely on guessing the answer, although sometimes you might be able to make it work out. Let's try to build a Hamilton circuit without guessing. And we're going to use this fact that I wrote. I had to scroll it away, sorry. It says, if some vertex has degree 2 in the original graph, then our Hamilton circuit must use both of those edges. So look at this one. Actually, I do see some vertices with degree 2. Though they are those 3, right? They have degree 2. And each of these vertices that are degree 2 must meet the Hamilton circuit along 2 edges, which is to say the Hamilton circuit has to go through those 2 edges. So that means if I'm trying to build it, I'm going to scribble in these 2 edges. The Hamilton circuit must use those 2 edges. I don't know, like for example, in the middle, I don't know which of those 4 edges it's going to use. But along here, it definitely has to use those 2 edges. All right, so here, this 2 means we must use both of these edges in our Hamilton circuit. We're going ham today. We have to use both of those edges in our Hamilton circuit, all right? And similarly with the other twos, right? I have this two here and I have this two here. We must use the two edges on right here, and we also must use the two edges right here and here. All right. So if your goal is to try to create a Hamilton circuit, here actually I would say you're almost done at this point. But this looking for degree 2 vertices tells you how to get started. Whatever Hamilton circuit I use must include all of these edges. And now it's almost completely done. I mean, to make a circuit here which uses all of the vertices, what are my choices? I mean, I could close it up by using that edge as my final edge, but actually then I would have missed the vertex in the middle. Instead, I think we should choose that edge, and that will finish it up. But actually, we can do even better than that. So I want to try to build a Hamilton circuit without guessing. I would say, first of all, choose all edges at the degree 2s. That's what I just did. Choose all edges at the degree 2 vertices. I don't know if it seems very simple what I'm saying right now. This topic especially, I think, lends itself to seeming really simple when I do it, and then I'm going to ask you to do an example, and you have not been paying attention. You will have no idea what's going on. So try to guard against that. I don't know what you can do to guard against that, but this looks very simple, and you have to sort of hold a lot of things in your mind. Anyway, first you choose all of the edges that meet at the degree 2 vertices. Those are those edges. Now, I can furthermore, now at this point, I think it's pretty clear to just look at it and say, oh yeah, to finish I got to just do that, right? That's how you finish. And fine, but I would like to do even more steps without guessing, because I don't like guessing in general. In this problem, it's fine, but this is a small, easy example. Even more things I can do without guessing. If you see any edges, for instance, right here, this is an edge now where I have already picked 2 edges going through there. That means I cannot use any more edges through this vertex, because every vertex, in the end, like when you're done, remember like I said up here, when you're done, every vertex has 2 red edges going through it. Some of these already have 2. That means I cannot use another one, and so I would say first choose all edges at the degree 2 vertices, and then we can, I will say next, disallow any edges that would make a 3-way intersection. What I mean by that is, for example, right here, I already have 2 edges there. That means I cannot also use this edge in my Hamilton circuit. That one is now out of bounds, all right? Right here is now not allowed anymore. That edge is not allowed. You can X out any edges which would have made a 3-way, all right? We do not like the 3-ways. I was at, for Easter dinner, we went to visit my parents in Boston, and my kid was talking about her friends, and she said, yeah, we got mad at my friends because the two of my friends were just hanging out with each other, and they asked my other friend to have a threesome. And my kid who said that did not know the connotations of that word. Yeah, it was a little uncomfortable moment. That's how kids be sometimes. I met a kid once. I think he was like in kindergarten. He said, "Hey, have you ever seen an adult movie?" I said, and as I was not sure what to say, he said, "Well, I have." I said, "Oh, really? What was it called?" He said, "The Dog Who Saved Halloween." All right. Yes, I've seen an adult movie too. Anyway, so first you choose the edges at any degree 2s. All right, then you will see some other vertices which already have 2. That means you can't use the other one. So right here, this would have made a 3-way. That means this is not allowed. Also this edge, right? For the same reason, right here, it would also make a 3-way if I chose that edge. So that guy is not allowed. Right there. All right. So when you're working this out, it's sort of a process of saying, okay, I must include these particular edges, and then because I included those ones, that means I must exclude these other ones. And then because I excluded these other ones, that means I must include some other ones. Check it out. The one in the middle now, I have already excluded 2 choices. That means there's only 2 legal choices, and so I must use those 2 legal choices, and then I'm totally done without ever guessing anything, all right? So now I say, first choose all edges at the degree 2s. Next, disallow any edges that would make a 3-way intersection, and then find some with only 2 edges remaining, and then choose those. And in this case, this is an easy example of what I'm doing now. Sometimes it can be a little bit more difficult. But in this case, this guy right in the middle, now at this point has only 2 options left, which means I must use those 2 options. So I can choose this edge and that edge. And now I'm completely done. I have the entire Hamilton circuit here without ever having guessed anything. That's the point of this, all right? Like I said, this small example, probably you could just guess it out of nowhere. But on our homeworks or on the tests or whatever, I'm going to give you a really big one that you could never guess the whole answer at once. But this is how you construct the answer little bit by little bit. That's the idea here. Any questions at this point? We're going to do some more examples. All right, let's try one. I got a bigger one. How about this? A little bit bigger. And there's an extra little vertex in the middle there, all right? So we're going to try to build a Hamilton circuit. Without guessing. Only by using these rules about 2 of the, I'm going to draw these in red, but 2 of the red edges have to touch every vertex. So if you see a vertex with only 2 edges on it, you got to use both of them. And if you see a vertex with where you've already used 2 of them, then you should exclude any of the others. Anybody got a suggestion of how we can start off here? Yeah.
I would just start on the corners.
Yes, the corners are all degree 2s, right? Whenever you see a degree 2, you can start by choosing those 2 edges. So I choose this one and this one. I choose this one and this one. I choose this one and this one. And this one and this one. Great. Any more degree 2 vertices? Yeah.
What is with the one in the middle where we start?
Yeah, this one in the middle. This is also a degree 2. I didn't intend for this to be the starting point. It's actually, when you're building these Hamilton circuits, you don't ever have to think about where I'm going to start. You just choose the edges and they will all connect up naturally. So yeah, this one in the middle there also is a degree 2 because it has 2 edges touching it. And so I got to use those 2. All right? Okay, so that's sort of like the first step. You choose all the degree 2 edges. Now, are there any edges which we can disallow because they would have made a 3-way? I think you can probably see some. Yeah?
2 like at the bottom that are cutting.
Yeah, these 2 horizontal ones are now not allowed anymore because this one makes a 3-way right here. All right. So it would not be allowed to use that edge. So I cross it out. All right. Now, having done that, are there any vertices that you see which have only 2 legal choices left? Yeah.
The ones next to the ones you just crossed.
Yeah, the ones on the other sides of these guys. Now, if I look at this vertex here, I've excluded this one, which means it has only 2 possibilities left. And so I must choose those 2 possibilities. Like so. Right? You fill those guys in because they now are the only alternatives at that vertex. And then similarly on the other side. It's like a little puzzle. There's something I feel like doing this is I have the same feeling as if I'm like playing Minesweeper, where it's like you make one little move and that tells you a little something about something, and then that helps you to figure out how to make one other little move, which then tells you a little more something about something. This you could probably turn into a cute little phone game or something. Anyway, can we continue here? At a certain point, you will just sort of realize what the answer is. I mean, the goal is to connect this up into a big circuit. Yeah?
One question, for example,
Sure.
when now the upper and the line on the bottom, they already have two like lines. So
Yeah.
is then the third line, can we cut them out?
This one?
Yeah.
Yeah. This line here is not allowed to be used because that
It
would
doesn't
make,
work.
you can't use that one.
And
I think it is possible to finish here.
how?
How about the one across the top? I would say the one across the top will make it work. If you want, you could say this, look at this edge, right? Right here, I'm now using two edges, which means I cannot use this one. And also right here, I'm using two edges. So this guy here and this guy here have two edges chosen, which means you cannot use the third one. So these guys are off limits, and then the only choice remaining is that edge right there. So this is my Hamilton circuit. It touches every vertex without repeating any. All right? That's the way that you find Hamilton circuits. In my opinion, much more complicated than finding Euler circuits. But, I mean, not super hard. All right? Any thoughts about that? I got one more trick. So everything that we've been doing here is based on the idea that every vertex touches two of these edges. One more trick is, and I will say it in just a few words, I will say this is my second obvious fact. There are no subcircuits. What I mean by that is your whole thing is just going to be one big circuit. It's not allowed for it to have parts inside of it which also close up and make circuits. Like, for example, your whole thing is supposed to look like this. You know, maybe like that. Like that, right? Not like that. This has what I would call sub-circuits, like this little guy here is its own little circuit inside of the larger circuit. That's not allowed. Really, it's because a sub-circuit requires some three-way intersections, which are not allowed. All right, so a Hamilton circuit has no sub-circuits. This you can also use to exclude certain edges. So here's an example where you also need to use sub-circuits. Sorry to scroll so much. Here is an example where you have to think about sub-circuits also. All right, how about this one? Let's find a Hamilton circuit without guessing. Actually, before that, how about with guessing? You just go around the outside edge, and that's a Hamilton circuit. But I want to try and reason this out without guessing like that. To find a Hamilton circuit without guessing, again, I'm going to begin with the degree 2 guys, which would be here and here. And so I have to use this and this. All right? So that's the simple starting point. And now I would like to disallow some other edges, but actually at this point, I can't disallow any because they would make a three-way, because none of those other edges would actually make a three-way. But I can say at this point, this edge would make a subcircuit. Right? If I were to use this edge, it would make a little circuit over here, and that is also not allowed. And so for that reason, I can disallow that edge. And similarly, on the flip side, I disallowed this edge because that would make another little subcircuit. So it's this little subcircuit which I'm trying to avoid, and also on the other side. All right. So this is one other trick you can use to cross out some edges, is if they would have produced a subcircuit. Okay. So having eliminated those two edges, now if I look at this vertex here, I have only one choice remaining. It must go across the top. All right. And similarly, if I look at this vertex on the bottom, I have only one choice remaining because I've excluded this edge. It must go across the bottom. So now it must, I'm just going to redraw this so I don't mess up my earlier picture. It must look like that and that. This is excluded, that and that. This is excluded, and now I have to choose the top and the bottom. Because at what I said, at this vertex here, I only had one legal choice remaining, and that was across the top. All right. This is how we do it. Any questions so far? I have some that I would like you to try. Can we try? Yeah, here's one. I hope this isn't too hard. I want everyone to try this one. This has some extra vertices in there. See what you think. You should begin by scribbling in the corners and also any other edges which meet one of these degree 2 vertices. And then kind of go from there by including and excluding some edges as you go. With no guessing. I suppose it's hard for me to tell on a test or something if you're guessing or not, but I'll just make it so big that you wouldn't be able to guess the right answer. I'll walk around and see how you're doing.
Isn't it just the perimeter if these guys can't fly?
No, your path has to get into the vertex. So you have to go in and get this dimension. And there's also some extra vertices. So there's one here.
Yes, so I'm glad it is.
You should start off by saying which edges you have to use those two because and so on. There's others. All right. I think something's going on. Otherwise, I might like it. Okay. That's a good start. You can also, like, these guys are also doing too. You got something? All right.
Oh, okay. Oh, sorry. Okay. Thank you.
You okay? All right. You got something? Yeah.
Before I did that, can you remove those two right away just because any of them were that I make a thing?
Okay, yeah. This, yeah, these guys are also trying to do.
Oh, so it doesn't matter if it's.
It's just any more than two. If you use that one, it'll make it
Oh, okay.
Alright.
X this one up.
I would say not. Yes. No. So these guys here, they are also twos. Because it's a one. So you can split those into get four. This one is. Does this work? No. Just twos. You shouldn't try to connect all to the rest because you don't know. Is it going to connect there or not this one?
Okay, wait, I guess I'm just confused at the three part, like, is that a three? And then that's what.
That's right, because, well, I don't know if it's constructed, I'm not sure why this is like that.
I was
But
just
here,
confused.
yeah, you shouldn't just connect.
Okay.
What, yeah. Yeah, it is.
Okay.
But like this, when you work,
We go
Okay.
now here.
boom, 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 boom,
It's
boom.
Okay, so then do I send this as three there?
Wait, no, that doesn't work. Just one
No,
straight.
because
Boom.
you might actually use that one.
I think that was a shade of
Yeah.
confused.
I would say what should happen next?
Do not match.
You should look here. This vertex probably has two edges that are joined. That means you're not allowed to use this one because that would be
Yes, wow.
you're not allowed to use this. Alright. Yeah, and there's another one. Let's talk about these. I see various, oh, sorry. Take another one.
Watch movie, right? She's like, actually, on this one, we're allowed to bet the rules.
You're not allowed to go through. You can only go along edges that are already in the picture. Yeah, so these guys should be chosen around the edges. That's because this corner only needs two edges. So you must use both of those. And then these dots also only need two edges. Wait, and so you have to use those two edges also. I'm about to. So let's chat about this. I saw varying degrees of success. Remember, the first step is to scribble in all of the edges at any degree 2s. Those would be the corners here, have degree 2s. That's why I scribbled in those edges. And also, these sort of extra vertices in the middle of these edges, those have degree 2s also. This is a degree 2 and a 2 and a 2. All right, that's because there are two edges which touch that vertex, whereas this one here is a 4, so you don't know what to do there next. Anyway, that means I'm also going to scribble in these, and these, and these, right? You have to use all of the edges which exist at any degree 2 vertex. Okay, I would say so far this is kind of the starting point where you scribble in all of the edges at degree 2 vertices. Now, I'm going to look at here and try to disallow certain edges. I saw as I was walking around, several people at this point tried to just like connect it up in a way that looks pleasant. I would suggest against this. You should not be just trying to connect the lines together because you might make a choice which ends up screwing you over later. Like for instance, if I'm looking right here, and I'm like, well, these guys ought to meet up because I think they're gonna eventually meet. Actually, that is a bad choice. The Hamilton circuit eventually we'll see does not go that way. In fact, this one goes here and this one goes here, but we don't know where it's going to go yet. So what do we do at this point? I'm going to look throughout the whole diagram to see if I can find any edges which would at this point make a three-way intersection, and I would disallow them. Or you could also look for any edges which would make a subcircuit and disallow them. And I think this one right here, this edge right here, is illegal at this point, because if I connected this edge here, first of all, it would make a little box like that, which is not allowed. That's a subcircuit. Also, it would make a three-way intersection right here, which is not allowed. So that means this edge right there is disallowed. All right. This can be difficult when you're, like, if you're taking notes right now, because if all you're looking at is the final answer, then you will lose track of all the steps that I did to get there. But I'm going to say this one would make a three-way intersection on its left side over here. If I had used it, that would make a three-way intersection, and so I'm going to disallow that. Maybe for the sake of making a clear presentation here, I'm going to, maybe I'll just copy this picture so that you can see step by step what I'm doing. When you're doing this on the homework or whatever, I would not expect you to redraw your picture over and over again, but just for the sake of me being clear, step by step for now. I disallow that edge. Does anybody else see another edge which would make a three-way intersection somewhere? Yeah?
No, because the where you put this one
Yes?
on the right.
Yeah?
Because this one is allowed, we have to draw it down.
Okay, sure. So this is, I was going to say X out another one that makes a three-way, but you could also look for edges or look for vertices where there are no more choices. You have to use the only one. And so right here, there's only one choice remaining. I must use that one edge right there.
And therefore, the other one to the left a bit, under the...
Yeah, and then you're going to X out this one.
Cannot be
Mhm.
because they're already fit.
Great. So I'm going to try and do this like one step at a time here. That one here, we must use this one. Since it was like, the way this picture looked like before was this. And there's only, you have to choose two edges at this vertex total. One of them was already chosen. One is illegal. That means you have to use this other one. All right? Okay, great. And then she said, the next thing she said was X out this one, because at this point, now that I use that guy, this would have made a three-way here. So now I'm going to omit that one. I'll copy this again, just so you can see each step one by one. So now I'm going to X this guy. That's because this would make a three-way. All right. Anybody see somewhere else which would make a three-way? Yeah?
On the right side between the two vertices.
Yeah, this kind of, this one right here? This sort of middle one on the right. Yeah, this also would make a three-way intersection up here if I used it. And so I can X that out also. You mind if I do two steps at once there? Yeah?
And the
Yeah.
in the top middle one?
Yes, and the one across the top. That also would make a three-way intersection right here, right? So I X out this one also. All of those. Is there another one?
And therefore, the other one to the left has to be used?
Yeah, right. So we can X out all of these because they would make a three-way intersections. And now we should look for, now that I've X'd those out, are there any edges that I have to use at this point? That would be an edge where there's only one way to go it. And so right now, this guy right here, I've used one. I have one that's not allowed. The other one must go like this. All right. So now we're forced into certain other choices. I'm going to trying to write this one step at a time. I'm going to copy this once more. So my next step is to choose this guy and others. How about this guy here? Right here, I had only one edge before, but I have two exclusions, and so the only other possibility would be to go down here. Right? So I chose this one and this one. we continue. It's the same process until you're done. So are there any that I can disallow at this point? I would say I can disallow this one now because it would make a three-way here, and also this one because it would make a three-way here. All right, here I have two that are chosen already, which means neither of these other ones is legal. So I X this guy, I X this guy. That means I must use this edge down the left. And then down here, this would also make a three-way right there. So I X this guy, which means I have to use this one. And that is finished. It's a big old H. H is for Hamilton. Isn't that cute? All right. This is how we do it. It is a little complicated, and it's quite difficult to explain step by step. Unfortunately, if you just look at this answer, it's not clear what were the individual steps that led you to this point. And as I was going around, some of you noticed, it's easy to mess this up as you're going. If you ever find yourself that you have created a three-way somewhere, then it means you messed it up at some point. Yeah.
I think like a good strategy to like stick by when you're trying to do this is like try to make sure like that you end up drawing like one singular shape.
Yes.
Which is sort of like the same thing as like avoiding subcircuits, but I think
right.
The singular shape thing is easier to visualize.
Yeah, maybe. Although I would say, yeah, that's true. I mean, really, however you want to think of this, as long as it works, is fine with me. Although as I'm doing these, I don't really try to imagine in my mind what this thing is eventually going to look like. Like it ended up looking like this H, but it's not really important that you think about what it will eventually look like, as long as you just go step by step. This is how I think through it. All right. One more thing, and then I got a couple more examples to try out. The same reasoning, so I can say we can use this reasoning to show that no Hamilton circuit exists. So actually on our tests or on the homeworks, I'm more likely to just give you a graph. Rather than saying draw me a Hamilton circuit, I'm more likely to say either draw me a Hamilton circuit or explain why no Hamilton circuit can exist. So we use the same reasoning though to show that no Hamilton circuit exists. For example, here's one that we said at the very beginning. This was one of the first examples that I showed you, an hour ago or so. This one has no Hamilton circuit. I said at the time it's not really easy to say why. Actually, we can say why at this point. You would just try to start drawing it. Try to start drawing it. But get stuck somehow. All right, for example, in this case, if I, first of all, choose the edges which meet the degree 2's, then I automatically end up choosing all of the outer corners. And now, actually, I've already made a complete circuit here, and it is now impossible to get here without creating a three-way, right? The only way to get to the middle would be to force a three-way somewhere. And so that's the reason why it's not possible. So you try to start drawing it. We chose the degree 2 vertices. But the last one, the one in the middle, the last one will force a three-way, and that is not allowed. So it's impossible. All right. This is the way that you can demonstrate that there is no Hamilton circuit. You make a few steps that you have to make in order to start it going, but you will find at some point you get stuck, and you're not allowed, or you're not able to continue. All right. This is how we do it. Here's another example like that. Here's one with no Hamilton circuit. Has no ham. I would try the same kind of thing. First of all, identify all the degree 2 vertices, and then scribble them in. So I would say, actually, I meant for, let's put some more dots in there. Anyway, this is where my degree 2 is at. Here, that's a degree 2, so I scribble there and there. Down here in this corner, that's another degree 2. And then this guy in the, each of these dots is a degree 2. This guy in the middle is a degree 2. This dot. And then I have corners here, here. Anyway, these corners don't really matter. These ones here, I have already been forced into a three-way. So you can immediately say this is impossible. Just by choosing the degree 2 edges, that immediately already created a three-way intersection, which is not allowed. So here, this one has no ham because choosing the degree 2s has already created a three-way intersection, and that's not allowed. All right, so that's the kind of situation in which you can say it's definitely impossible. Because I was just following the rules and it automatically created an unallowable situation. All right, I got one more example of a big one where it's impossible, and then I have some examples for you to try, and that'll probably do it for us. This is a cute graph of a grumpy guy. So let's say there's a vertex up there. And we got some of this. I was very pleased with myself when I came up with this graph. It's silly. Let's say there's a vertex there and there. Those are like the eyeballs. All right, this is my grumpy guy. Your job is to either draw in a Hamilton circuit or explain to me why there is no Hamilton circuit. So you should start by just trying to make it work and see if it eventually does work, or maybe you will somehow be forced into an illegal configuration. That's the idea. So we should begin by scribbling in any degree 2 vertices. Does anybody see any degree 2s? Yeah?
The nose?
The nose, yeah, the two sort of points of the nose, that's a degree 2 over here and over here, right? So that means I have to use these guys and also that one. Any other degree 2s? Yeah?
All the way up to the top there.
Yeah, the very top, that's a degree 2. So I got to use these edges. Any other degree 2s? Yeah?
Maybe the circle. In the circle, like not the hole, but
The circle.
the two eyes.
Yeah, these guys. Yeah, these are degree 2s here. The two eyes, if you will. All right. So this is a start. I think those are all the degree 2s. This is a degree 2 here and here. All right. Are there any places that I can disallow an edge because it would make a three-way intersection? I think there are some. Or perhaps because it would make a subcircuit. Yeah?
The line, like above the nose. Kind of.
Yeah, the line connecting across the top of the nose, this would make a subcircuit, the little nose. That's not allowed. So that is disallowed.
Wouldn't the frown create a subcircuit?
So the frown would, although that means you can't use the top and the bottom of the frown. But it doesn't mean you can cross out the top, because you can use the top. Just then you can't use the bottom. So yeah, you can't really say much about the frowny part. Are there any other edges now that we have to use or can disallow? You got an idea?
The where you just crossed out to the left and to the right have to be used.
Yes, she said like this. Because right here, I have already, right here, come on now. Here, I'm gonna zoom it. Right there, right? we have, this is a three-way junction in the original graph. I've disallowed this one, which means I must use that one, right? Because we have to use two of these edges, and one has already been disallowed. So I must use that guy right here. And for the same reason, on the other side of the nose, you have to use that other little guy right there. All right. Any more? You want to just keep on looking for other edges which you can either say I have to use or I cannot use. Yeah?
Not be able to make a three-way there, looking where it's
Yeah, on this eyeball thing here, I have already chosen these two edges, so I cannot also use that part. So this part gets a X. Similarly on the other side, gets a X over there. Okay. Getting somewhere, maybe. As long as you are making new deductions about either choose an edge or eliminate an edge, you are making progress. I got it. What do you think?
Like the bits on either side, so where you have the two lines going like this.
Yes.
The line like at the top in between them on both sides. I don't.
This guy?
Yes. I don't think that would be allowed.
I don't know about that. I would say this, if I used it, at least at this point, it would not immediately make a three-way or other illegal. I think there is something you can say about that area, yeah.
That vertex right there needs that one and the one underneath it in order to have two.
Yes, this vertex right here, it has three edges, but actually one has been disallowed, which means the other two must be used because every vertex needs to use three edges. So this one right here, I've already disallowed one of the edges. I have to use these other two. So I got to use that one. I got to use that one. And then same idea on the other side. This is all symmetrical. So on the other side, I must use this one and also that one. Ooh. Yes?
And therefore the lower line of the glasses
Yes.
are not allowed because we already have two.
Yep. That's right. Yeah, this would make a three-way. Actually, we don't even need to say that. I think actually already there's something illegal about this picture. Anybody? Yeah?
It's a subcircle.
Yes, this has already made a subcircuit. All right? And I wasn't trying to make a subcircuit. I was just following the rules, and it automatically made a subcircuit. And so we can stop at this point and say the whole thing is impossible on this picture. All right? So this one, we were forced into a subcircuit. Now, she said, you know, there's still more that you could do here by excluding and whatever. Eventually, you might find a three-way somewhere else or something, but we might as well stop at this point because we've already made a subcircuit. All right, so a Hamilton circuit is impossible. Exclamation. All right. In our remaining 10 minutes, I got two more for you to try. I don't know if we have enough time to do two more big ones, but we can, we can try them. How about, actually, let's just try one. Your job for each of these two is either find a Hamilton circuit or explain why there can be no Hamilton circuit. I had two, but let's just try one. We'll do the other one when we come back next time. Find a Hamilton circuit or say why it's impossible. All right. Same procedure as we've been doing. I'll walk around and see what you think.
This is a charge.
Yeah, but then if I went down here, that would make a subcircuit there. Then that would make a subcircuit. So, yeah.
There's other to say like a little cleaner, I would say this vertex. And then that means here, if that's excluded, I must just also that. Can we talk about it? I see some people, so I believe the answer is no, there is no Hamilton circuit here because, well, let's say why. I would begin by scribbling in all the edges that I know I have to use. That's a degree 2, that dot in the middle there. Also here, here, and then these two corners are degree 2s. Like so. So this is what you sort of begin with. You have to use all of these edges. Now, I would look for edges to exclude because they would make three-ways. And I can see actually a lot. Like for example, right here, I've already used these two edges, which means these two must be excluded. So I can cross off that one and that one. I could also say, for instance, right here, I've already used those two edges which are used, which means the other two are now illegal. So I can X out here and here. There are many ways to finish this off. I would say at this point, this edge right here, I have used one, excluded another. That means I must use this edge right here from the corner. But then I have created a three-way right there. Probably if you were doing this, you wouldn't get exactly the same route to a disallowable configuration, but there are many ways to reason this out. But this is how I would have done it. So anyway, it's impossible. So this, when I did it, I was forced into a three-way, which is not allowed. All right. I hope you said something like that. We do have 7 more minutes. How about we just try to do all together this other example that I was going to do. This one, I believe, does have a Hamilton circuit. It looks like that. All right, let's see if we can find a Hamilton circuit in this one. Again, without guessing. This one, I think, does have a Hamilton circuit. So I should begin by scribbling in all of the degree 2s, which would be these kind of corners, and also that dot in the middle is a degree 2. So I am going to use those edges and then also around the corners. Around the corners. These corners here, these corners here. All right. So this is my sort of where I get started. Now we should be crossing out some edges which would make three-way intersections. I can see, say right here, that's now, there are 2 chosen, so I cannot use this third one. Also, just below it, this edge. So these guys are not allowed because those are 2 that would make three-ways. I see another three-way right here, right? This also right there has 2 edges which are used, and I should disallow the third one right there. All right, anybody see anything else I can go with at this point? Either crossing out an edge. I actually see one edge here which I can cross out because it would make a subcircuit. Anybody see what I'm thinking of? Yeah?
Over there in the bottom right.
Yeah, over there on the bottom. This guy right here, if I use this one at this point, it would make a little subcircuit right there, which is not allowed. So this I can X out. I think those are all the X's that you can say at this point. Anybody see, now that I've made those X's, are there any edges that we must use at this point? You should be looking for a vertex where there's only 2 legal choices. Yeah, someone has given me hand signals, which I think is indicating this vertex right here. Nope. Oh.
I was indicating an edge, like the little enclave, the little crawl space.
Here?
I don't even know what an enclave is. No, it's to the right.
This one?
That edge on the bottom. Yeah.
This, you have to use that?
I think so.
I don't know about that. I don't think so. I mean, maybe, but at this point it's not clear to me. What about the blue one? I like the blue one there. The blue one has only 2 legal choices left at this point, right? I crossed off, there were originally 3 edges here, but I crossed off one of them. That means I have to use the other 2. So I'm going to use the other 2 edges there. And then a similar situation exists right here, right? There's only one more possibility at this point, so I have to use this guy here. Huh? How you feeling now? What else?
Then it is not possible. You can cut the one to the left, in the middle left.
This one here?
Yeah.
Yeah, this is not allowed. That would make a 3-way down here. It would also make a little sub-circuit. Also, this guy is not allowed because it makes a 3-way here. Is that what you were going to say? So, X that, X that. All right. Now I think looking at this vertex, I've X'd out so many that I have to continue up here. There's no other way to do it. Coming out of this vertex, it must go up. Also over here, I've X'd that one out, which means I must use this one. And then to finish it off, this guy, I cannot go up like that because that makes a sub-circuit, which means I have to go across here and across the top. That's my answer. That hits all the vertices. All right. You'll have some practice with these on the homework for next week, not this time.